In this video, I explain the quasi-static process by using these various animations of the piston cylinder arrangement as well as for the PV diagram, so you can easily understand it. Quasi-static process has the generally two characteristics. It is the reversible process and it is the slow process. So first we understand the definitions of the quasi-static process and then understands by taking the examples of piston cylinder arrangement. Quasi-static process means when process means it is the any process. Okay, you know that there is a various type of cycle is there. In a cycle there is a number of process. Okay, so process proceed in such a way that system remains close to thermodynamic equilibrium state at all the times, and it is called as the quasi-static process. Okay, means in a cycle number of processes is there. Okay, during this particular process the system remains close to thermodynamic equilibrium. So here you at least know what is the thermodynamic equilibrium, then you can easily understand. Thermodynamic equilibrium means system must be or compulsory in thermal equilibriums, in mechanical equilibriums and in a chemical equilibriums. That I already upload the video on thermodynamic equilibriums, and the link for thermodynamic equilibrium is provided on a top right screen of your mobile from the I symbols. Thermal equilibrium means temperature inside the system is remains constant on all the state. Mechanical means force is same at all the state of the systems, and chemical means there is a no chemical reactions which change in a time. It is called as the chemical equilibriums. Okay, so these system are in thermal equilibrium state at all the times. It is called as the quasi-static process. So now let us consider a system of gas contained in a cylinder as shown in this figure. Okay, so first I explain you the non-quasi-static process, then we move towards the quasi-static process. So by using this figure, here you see this is the cylinder. Okay, inside the cylinders the piston is reciprocate due to the pressure of the gas. So this is the initial condition of the piston, and we give the number 1 to these initial positions of a piston. Inside this cylinder piston arrangement some gas is filled it, and we consider that it is the fast expansion process is carried forward. Means due to the expansion the pressure is reduced and the volume of the gas is increased, and we put the certain weight on the piston to balance the force applied by the gas. So if the gas is compressed, then its pressure is higher, so gas is applied some force on the piston, and piston is try to move in upper direction. Okay, so when we put certain weight the piston is not moving upper direction but it is on a state positions, and here two stops are provided. Means stop seats limit the upper positions of the piston. Piston are not able to move ahead of this stop. Now system is initially in equilibrium state, and it's described by the property P1, V1 and T1. P means pressure, V means volume and T means temperatures. So this is the initial position 1. At that initial position 1, this gas have a certain pressure. It is denoted as the P1. Its volume is denoted as the V1 and its temperature is denoted as the T1. Now this state number 1 is plotted on the PV diagram. So pressure on the y-axis, volume on the x-axis. Okay, so during this initial position it have some pressure. Suppose we consider it is the 6 bar pressure. Okay, so at this point the value of pressure and volume is 0. When we moving in upper direction the pressure is increased, and on x-axis we moving on the right direction, volume is increased. Okay, so we consider that is a 6 bar pressure and volume is the 1 meter cube. Okay, so what we draw? We draw the one horizontal line from the P1 point and from the V1 point one vertical lines. So both these point is intersect. It is our state number 1, and it is in the equilibrium conditions. Why it is in equilibrium? Which equilibrium? It is in thermodynamic equilibrium. Means during this state, means these initial positions, the temperature at all the point is same, force applied by the gas is same, that is called mechanical equilibriums, and the chemical is also equilibriums. The upward force exerted by the gas on the piston is balanced by the weight W on the piston, that I already explained. If the weight is removed, there will be an unbalanced force between the system and the surrounding. Now we remove this weight W, then what? That is unbalanced force is created, means here some different pressure is there, here different pressure is there. Okay, so this gas is apply certain force on the piston, and due to this gas pressure the piston will move up to the top, means here you see that is the new positions of the piston, and this gas is expand. Okay, so it is the expansion process. Here what happened? Initially volume of the gas is this, now here the volume is increased. Okay, so where is the point number 2 is coming? It is the right side from the point V1, and due to this expansion the pressure is reduced. So here 6 bar pressure, and after the expansion the pressure is suppose 1.5 bar, so line point is come towards the downward directions. So point number 2 means here first we denoted on this image, that is the point 2, that is the final positions of the piston after removing the weight. The system again come to the equilibrium state, which is described by the properties P2, V2 and T2. Means after final positions, piston is again come into the system is again come into the equilibrium state, and this equilibrium state is described by the pressure P2, volume V2 and temperature T2. Now the pressure is reduced, so point 2 is come in a downward direction, and the volume is increased, so it is move on the right direction compared to the V1. So we draw the one line from the P2, one line from the V2, and we get the point number 2 here, and this is the state 2 in a equilibrium conditions. Now we connect these two point by one line. Okay, this is the intermediate state and non-equilibriums. Okay, so here we are able to draw this line any direction. We are also able to draw straight line, we also draw this type line, because we are not knowing the intermediate state. Okay, but the intermediate state passed through by the systems are not equilibriums, and it will be not possible to describe the part. Okay, so we are not knowing the intermediate positions, and due to that we are not able to denote the proper part. Okay, but we draw this type of the lines. Thus the process 1 to 2 is the non-quasi-static process, and it represented in a blue line on a PV diagrams. Okay, means this is the non-quasi-static process because we are not knowing the intermediate state, and if we are not knowing intermediate state, then we are not saying that on every state the system in a thermodynamic equilibriums. Now before moving ahead, I request to like the video and subscribe my channels for watching the more video related to the mechanical engineering. Now if above process 1 to 2 takes place slowly, okay, so earlier process is very fast, when we remove the weight it is suddenly moved, but we do this process slowly, and each step there is only a infinite simple changes in a properties. So it is possible if the single weight on the piston is replaced by the number of many small pieces of the weight as shown in this figure. Okay, so how we make this process slowly? By dividing the weight into a number of small weight. Okay, now here you see this is the new diagram. So here you see that is a different small weight is put at. Suppose earlier we putting the 7 kg of weight, now it is divided in a 1 kg into 7 weights. Okay, so here the weight A, B, C, D, E, F, G are available. Okay, so here you also see that is a specific state we can find out. Okay, so here A weight, B, C, D, E, F, G weight are put in. First we remove the weight A, then after we get the one state. Okay, then after we remove the B. So this process is occurred slowly. Now these weight are removed one by one very slowly from the top of the piston. So first we remove the 1 kg weight A, then the piston is slide move in upper direction, so slide pressure is reduced. Okay, and the slide volume is increased, so we get this point number A. Okay, so by doing this method the process speed is reduced, it is done slowly, and we are also able to get this intermediate state which are in the equilibriums. If the piston is moved slowly, the molecule will have the sufficient time to redistribute. Okay, when the piston is moving fast, then what, they have not sufficient time to redistribute. As the result, the pressure inside the cylinder will always be uniform and will reduce at the same rate at all the location, means at all the point inside this gas they are reduced at the same rate, so we can achieve the thermodynamic equilibriums. So every state passed through by the systems will be in a equilibrium state. So after removing A, we get the A state. Then after we remove the B weight, then we get this B point. So similarly we proceed removing the 1 by 1 weight and we get this complete process. So such a process pass through all the equilibrium point is called as the quasi-static process. Okay, so here you see that is all the state are in the equilibrium condition. Okay, that's why this process 1 to 2 are called as the quasi-static process. A quasi-static process is also called as the reversible process. So if we putting the 1 by 1 weight again, okay, in this earlier what we doing, we remove the weight. Okay, now similarly when we start to putting the certain weight, the same weight is compression of the gas is occur and they are follow the process from the state 2 to G, F, E, D, C, B, A. It is called as the reversible process. The main characteristic of this process is the succession of equilibrium state and infinite slowness, means the system is running too slow and they are achieve the equilibrium condition on all the state of the system. It is called as the succession of equilibrium. Static equilibrium process is an idealized process and is not a true representation of an actual process. Okay, means any system or any system actually are not follow the quasi-static process. Okay, if some system is followed, they have a certain errors. Okay, but many actual process closely approximate it and they can be modeled as a quasi-static equilibrium with negligible error. So some process is possible quasi-static, but we need to remove the some error from this system. The quasi-static process produce the maximum work or consume the less work. Okay, so we are achieve the maximum efficiency in quasi-static process because they produce the maximum work and consume the less work. So this process serve as a standard to which actual process can be compared. So thank you for watching this video. If you learned and like the video, subscribe the channels and don't forget to share with your friends.